So continuing on with homework number 23. Let me close my door. All right. So the U-Hearts Dynamic Club, they decided to go bowling, and this bowling ball looks pretty surprised. That's what I thought. So we're picking one of the bigger balls, right? The 16 pounds. That's one of the. I think it's usually this size. Maybe somebody can get the little kids ball. Play with that. It's 8.5 inches with an initial velocity of 25 feet per second and backspin, so it's going the opposite direction from what it would spin if it was rolling. 86 RPM down a polish lane, and so the kinetic coefficient of friction is 0.1. I want to treat the ball as a uniform spear, even though I just recently learned when doing research on bowling balls for this problem that they are not generally a uniform piece. So let's see. Here is my depiction of the problem. So one of the first things I might do is get the moment of inertia, and we want to look up what that is. And do I have a book nearby? Sure do. And in this book, it's harder to find in the big book, right? The big, huge version of the thing, the statics and dynamics combined. In the other one, it's in Appendix B, I think. This one, I think, is in Chapter 9 somewhere. And mass moment of inertia. You got area moment of inertia. And I think mass moment of inertia is later. Yeah. I should tab it. I should put little tabs in my book. Keep forgetting. Okay, here you go. So this is table 9.8, and here's your sphere, and you need 2/5 mass times. They call it A, but it's the same as the radius, right? So, okay, so we have to do a couple of units conversions here. So there was a 2/5 m. I'll call it r squared. So 2/5. The mass is 16 divided by 32.2. Turn it into slugs. And then the radius, so we're going to get 8.5 divided by 2, but it needs to be in feet. So square it. And what are we going to end up with? 0.02. Let's see, I'll do it myself here. 8.5 divided by 2 divided by 12. Square it, boom, multiply it by 16 divided by 32.2 divided by 5, multiply it by 2, and hey, I get it. I guess I'll go this way. All right, 2, 4, 9, 3, and these are slug feet squared. Great. Okay, and what else do I want to do now? I think I'm okay for here. Let's draw our little diagrams. All right, so first off, let's see, how big am I going to make? I'm going to have initial, impulse, and then final. So here, I'll draw it this size. Here's our initial, here's our impulse, and here's our final. Boom. And I don't know why I can't, there you go, zoom, focus, words. All right, so this thing has mass times velocity 1, and it's rotating in the opposite direction from what you would think, right? So it's going this way, I omega 1. Now the force is acting on here. We have the weight, we have the normal force, and now the friction force. And this is always something that, we got to always be thinking about this, right? So here I use a paper towel roll, right? If this thing is spinning that way right here, right, it is rubbing on the ground, right? So I'm making it rotate. For me, it's counterclockwise, right? And that means it's going to rub that way, so that means the thing is pushing on it in that direction, right? So you have to try to reconcile that yourself any way that you need to, right? But I think by going through that process right there to see which way it's going to rub, and then so which way the other thing is going to push on it. So one way you could think about it is that friction force is the thing that's going to make it want to go clockwise, even though it's starting out as counterclockwise, right? So eventually we're going to have mass and velocity 2, and we're going to have I omega 2 coming in that direction. And we're going to figure out the time that it takes so that what happens here is that this becomes the instantaneous center of rotation. Right? It's not right here, but it is right there. Right? So I'm taking a peek over at this other thing. What we're going to say is the system momentum is going to be equal to this. Well, now we could figure out the system momentum. Let's write this: system momenta 1 plus the impulse, or maybe we should say the external impulses. And oh, by the way, all these have to be delta t. I forgot, because this is an impulse diagram. It's not an FBD. Although it's treated like an FBD. It's an FBD with impulses, right? So we want all the forces that are external onto the thing. External impulses from 1 to 2. It's going to be equal to the system momenta 2. So I guess we could do this in the y direction. We're going to say 0 things going on in the y direction, plus the normal force times delta t minus the weight times the delta t is going to be equal to 0. Right? So this is sort of trivial, but we could cross out this. So we say that we know the normal force is equal to the weight, which we know is equal to 16 pounds. Duh. But from that, we can find the friction. So that's the kinetic coefficient of friction times the normal force. And so that's 0.1 times 16, and we get 1.6 pounds. Easy, 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 I know. But now in the x direction, we're going to say mass times velocity 1 minus friction force delta t, right? So this is linear momentum. Nothing else is in the x direction. It's going to be equal mass times velocity 2 in the x direction. So we don't know this time yet, but we do know a couple of these things. So so the mass is going to be 16 divided by 32.2. The velocity is 25. The friction force is 1.6. Delta t is something we're going to want to find out. We have our 16 divided by 32.2, and then we have this unknown velocity 2, right? So let's start with the velocity. Let's save this. Let's get this in terms of the velocity of 2, right? So that's going to cancel that out for here. So it's just going to be 25. But now it's going to be minus. So we have to divide this 1.6 by 16 divided by 32.2. So 1.6, 16, 32.2, divide, and then divide, and surprise, surprise, you get 3.22, right? It's kind of obvious that that was going to happen, I guess, in hindsight. But that's going to be equation 1. No, not V, it's T, delta T. Okay, so now we want to go to the angular, right? And I guess maybe, yeah, we're going to do it about the, let's do it about the center of mass. Yeah, that's going to be the better way to do it, I think. All right. So, and I could write this plus sum of the moments about, I guess I'll write center of mass this time. So it says I'll write G times time is going to be equal to I omega 2, right? So that's fair. We don't need to do the thing. Like if we were to take it about right here, which would be kind of interesting thing to do. Yeah. I need this omega 1. I was given it in RPM. I guess I was trying to be clever. So I need to have written that somewhere. I guess I'll do it within here. That's fine. So we got the moment of inertia. We calculated that of 0.02498. And noteworthy, it is going to be positive here because it's counterclockwise. And maybe I should put that in there somewhere. I don't know. So we had 86 revolutions per minute. So we want 2 pi radians per revolution. But we also want to divide it by 60 seconds per minute. Right? We need to get the units correct. Okay, so the moment that's going to be placed on it is actually clockwise. So it's going to be negative, and it's going to be the friction force. So I should have done this in symbols, but that's okay. I didn't. I think maybe you can understand where we're doing it for. 1.600 times delta t, but that's going to be times the radius of this thing, which I never calculated, so it's going to be the diameter, 8.5 divided by 2 divided by 12. And that's going to be equal to I 0.02498 times omega 2. I'll keep it right there. And we have used up enough paper. Sometimes when you cut this thing off right there, I don't like it when it gets that way. So this is page 4. Page 4. And this is 2 continued. ... And let me get all my values in here. 0.02498. 86 times, well, let me see what that 86 turned out to be. 86, 86 times 2 times pi divided by 60. Ooh, 9.005 radians per second. Times our 0.02498. Boom. And we want to get this, I'll just write it out for the time being. 0.22497, too many sig figs, minus our, this times the delta t, so 1.6 times 8.5 divided by 2 divided by 12, and so we get 0.5667 delta t. It's going to be equal to 0.02498 omega 2. Now we want to change. So this could be our second equation, I guess. But we also know a relationship when we get to this position right here. We're going to be able to use an ICR at this, right? So at the condition when it stops, when it's rolling without slipping, that does become the ICR. So here's the ICR onto the thing. So here's omega 2 and V2, and therefore V2 is equal to omega 2 times R, or omega 2 is equal to V2 over R, right there, right? So we could plug, we could say omega 2 is equal to V2 over 8.5 divided by 2 divided by 12, right? So at some point we could have done this. So we could have written out the thing. 8.5 divided by 2 divided by 12. So that comes out to 2.824 V2, right? So we can call that equation 3 if we want to. 1, 2, and 3 together. Well, no, actually first just let's go 2 and 3. And let's solve this for that velocity, right? So that's the reason why I'm putting this in here. So I'm going to go 2 and 3 together. Sometimes it helps me to just write them all out again. So solve for V2. Ooh, it's gonna be kind of a mess. Yeah, oh well. Oh well. 0.02498 times that. It's not too bad. So I'm going to divide both of those by this value. I'm going to save it. Okay. 0.56666. Boom. That becomes 8.034 delta t. And the other one is 0.22497. And so that becomes 3.190 right here. So we can call that 4 if we want to. So then we go 1 and 4. And 1. I was telling me my class is starting. It's not. We cancel. All right. We're going to set them equal to each other, right? So we have 25 minus 3.22221. Oh yeah, no, I got that delta t. Okay, good. Is equal to 3.190 minus 8.034 delta t. If we get negative time, I'm going to scream, but I think we're going to be okay. Maybe. I hope. I think I'm going to get negative time. I must have done something wrong with my math. Pause for the cause. This should be a negative value right there, right? So that should have been negative, which would have made this negative right up here, right in there. And so 2 and 3 would have made this negative, which would have made this, where'd you go? 2 and 3, so 2 here, and so this should have been negative, so that should divide both of these, should make that positive and this negative, and therefore when we got down here that was positive and that's negative. So okay, good. So we're gonna, this is gonna jump over here and add to that, that's gonna jump over there and add to it. Thank you. See, this is something that these signs can really mess you up. So what we're left with is 25 plus that, right? And then 3.22 plus 8.034, and divide them out. Want to double check my answers. I don't like it. with something weird where I multiplied instead of added these two together. So anyway, delta t is equal to 2.505 seconds, right? And so that was the thing we were trying to get. That was part A. Part B was the velocity at that time. So you could plug that into either one of our equations, either equation 4 or equation 1. I prefer equation 1. So I go 25 minus 3.22 times our 2.505, and so 3.22 times and then 25, and so what we end up with, V2 is 16.93. These are feet per second. All right, so the answer's A. The time, let's call it 2.51 seconds, and B, velocity 2 is going to be 16.9 feet per second, and going that way, right? Now, it is possible to make this thing reverse, but not without a whole lot of backspin and a whole lot of friction. But you probably have seen golf balls do this if you watch professional golf, and if you're an old man and you enjoy golf, you might watch old golf, and I enjoy watching golf. And backspin is a pretty impressive kind of thing to do, and they were able to get that backspin. I've only done it a couple times, and it was basically on accident. Can't do it when I want to do it, and sometimes it's actually kind of bad, so whatever. We'll see. All right, on to the last problem. Boom, 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 boom.